Hi, in this presentation we're going to talk about the main effects chapter, which is primarily about how to interpret and understand the beta coefficients and the effects that you get from a multiple regression model. First of all, we'll start out with some of the background data that we'll be using in our examples. It's the Fuel 2001 data from the ALR4 package. I believe we've seen this previously in the text. We're going to be talking about a model M99 that is a multiple regression model explaining fuel consumption per person. That's gallons per person. That's the variable fuel. Income is in thousands of dollars per person. Tax is cents per gallon. Driver's license, and then log of mileage. And this logarithm is in log base E 2.71, and we get these estimates from the output. And so we're going to talk about what these estimates mean, how to interpret them. First of all, here's a re-expression of the function that was on the previous page, and you can see that the intercept was 154 something, and this is usually not interpreted, but just for the record, the units of this intercept are going to be in the same units as the response variable. So in other words, gallons per person. The other coefficients, the other beta hats, are as rates of change. And so for example, the multiplier for tax, the negative 4.23, is the estimated decrease in fuel consumption for a 1 unit increase in tax, all other variables in this model held constant. And so the value you get there is 4.23, and that is going to suggest a reduction in 4.23 gallons per person for an increase in the tax of a cent per gallon. Just so we're clear about the beta hat for tax, there are units associated with that beta hat, and it would be in gallons per person per cents per gallon, so that when you multiply by a cents per gallon, you get your remaining units in gallons per person for the response. So this is what the units are for the tax coefficient: gallons per person per cents per gallon. As income would go up by $1,000 per person, you'd expect a decrease of 6.14 gallons per person, other predictors held constant. And so therefore this coefficient is going to be in gallons per person per $1,000 per person. Okay, we've talked about the tax estimate. One way you could think about this issue, holding other variables constant, you could explicitly say, well, holding them constant at their average values, or the X bars for all the other predictors, you could, we saw that that's a 4.23 gallon per person reduction, all else held constant. You could write that in terms of the coefficients like this. You could have an estimated mean function for fuel consumption as a function of tax varying and the other predictors held constant, designated by X bar 2, and you could just plug in the average values for all the other predictors and get a new estimated intercept and linear function that has this negative 4.23 slope in terms of tax. You could visualize that with the effect command from the effects package, and you could plug in a model, our M99 model, and the coefficient that we want to examine, tax, and this is a visual representation of what we see here from this estimated mean function. We see an intercept of 607 gallons per person, nearly, and then we see the negative slope with respect to tax. The shaded area sort of gives us an idea about the uncertainty in the fuel consumption values at the different values of tax. you'll notice the little markings down here on the horizontal axis for tax. Those are the values in the data set. So those are the observed values for cents per gallon fuel tax. They can see very clear evidence of a negative pattern. Here is the income effect from the effects plot, and you can see a similar sort of thing. As state income increases, we tend to have lower fuel consumption per person. And you can see the shading giving the level of uncertainty in the fuel estimates. So that gives you an overview of how to interpret parameter estimates. So make sure you understand that we're talking about a rate of change given other predictors are held fixed as what a beta hat coefficient means. Keep in mind that this is presuming or assuming that you can hold other variables constant and change the regressor that you want, and that's often not reasonable. For the example that we've talked about, the fuel data, this was observational data, and the predictors and the regressors were not under investigator control, so we really can't legitimately speak about changing a predictor or a regressor. Like, for example, we really didn't ever change a tax rate and observe a particular decrease in fuel consumption. We would really have to make a change like that and observe what happens to fuel consumption to really give a full causal interpretation. Keep in mind also that the effects and the estimates change depending on what other predictors are in the model, and that happens because the regressors and the predictors are correlated with each other. And these present some interpretational challenges because models can have different pieces of regression information in it. Here's another data example from the Berkeley Guidance study for girls data. We're going to have soma, or somatotype, be the response variable. Recall that that is a variable that higher values tend to mean a rounder body shape and smaller values tend to be a more vertical angular body shape. And we're going to use weight at age 2, weight at age 9, and weight at age 18 to describe somatotype. And before I move on to the next overheads, I want you to notice these three scatter plots. The first one here in the second row, third column, is a scatter plot that relates weight at age 2 with weight at age 9. And you can see that girls that are heavier at one age tend to be heavier at the other. Positive association. Same is true for weight at age 2 and adult weight. Tends to be true that girls that were heavier at age 2 also tend to be heavier at age 18, and a very strong pattern between weight at age 9 and weight at age 18. These three predictors are very correlated with each other. You can see there is some relationship with somatotype as well, but the crucial thing for this investigation is the interrelationships between the predictors. Here is a model that has all of those three predictors trying to explain somatotype, and the crucial thing to notice about this multiple regression model called M1 is that the coefficient for weight at age 2 is a negative value and is nearly significant, 0.065 p-value. And this is very disturbing because it's suggesting that holding the other weight predictors constant, increasing age 2 weight is associated, some evidence that it's associated with a decline in somatotype. And that just doesn't make any sense given the problem and the data that we've been looking at. And I want you to know that this really silly and implausible negative coefficient is happening because all of those weight variables are very correlated with each other, and it really can adversely affect the signs and the directions and the message from some of the coefficient estimates. Here is a way to address this problem. Use the same information about weight at age 2, 9, and 18, but create a new arrangement of the predicting information. So here I've created two new variables, DW9, which is the subtraction or the difference in girls' weight at age 9 compared to what it was at age 2. How much weight increase has there been from 2 to 9? And the same kind of variable, DW18, which is the difference or the increase in weight from age 9 to age 18. And these variables contain and are based on exactly the same information, but they are going to produce a predictor set that is going to be less correlated compared to what the original weight variables were correlated with each other. There's going to be less intercorrelation between the regressors. And what we're going to find is that if we use these things in multiple regression models, you're going to get very similar residual sums of squares and R-squared values. They'll be exactly the same actually, because the predicted vector y hat will be the same. But you'll get some slightly different coefficients and better behavior. Here's a scatterplot matrix of what I'm talking about. So instead of weight at age 2, 9, and 18, we'll have weight at age 2, the difference in the increase in weight from 2 to 9, and the increase in weight from 9 to 18. And if you compare to what this looked like previously on the previous scatter plot, you'll see that these, particularly these two scatter plots, are much less positively correlated with each other. And this is going to improve our estimation and interpretation. So here's model 2, the one I was talking about. We have weight at age 2 as a regressor. We have the increase from age 2 to age 9 and the increase from age 9 to age 18. And you will notice that our weight at age 2 variable still has a negative coefficient, but it is not nearly significant at all. And this is a much more reasonable biological system. I think you could understand that if you understood how much weight gain there was from age 2 to 9 and from 9 to 18, and if you held that constant, the impact of what happens to a girl at age 2 probably is not very substantial on somatotype. And so I think it makes sense that we get estimates like what we have observed here in model 2. Much better interpretation and estimation result. You might think about adding all of the weight and the difference in weight variables to a model, and I want you to observe what happens if you do that. If you add all of the component variables plus the two derived DW variables, you will notice that the model rejects the additional variables. They are redundant linear combinations of the original set, and they're dropped from the models. So here's an overall summary on overhead 16, and I want you to notice a few things. First of all, 70 observations in all of the models. The R-squareds are all the same because the y hat predicted vector is all the same. The sigma hat residual standard error estimate is all entirely the same. You will notice the beta hat naught, beta naught hat for the intercept is entirely the same. The values in parentheses are standard errors. And you can observe some things here. Weight at age 2 is the same estimate in model 1 as it is in model 3. And the weight, and the reason model 1 and model 3 are basically the same is we kicked out the DW coefficients and they weren't even estimated. So model 1 and model 3 are essentially the same. What I want you to notice though is you get a slightly different estimate for weight at age 2 compared in model 2 compared to the other ones. And there is really different regressor information in those models, and so we get a different kind of interpretation from it. We don't have coefficients for DW9 and 18 in model 1 or in model 3, because they did not appear. Notice the values for those weight gains are positive and they are significant, meaning that if a girl has a increase in weight gain, either from 2 to 9 or from 9 to 18, it tends to clearly increase their somatotype. So the conclusion about weight at age 2 differs depending on whether we're using Model 1 or Model 2. In Model 2, we got no evidence that it's associated with soma, holding the other variables constant, and I think that's quite reasonable. Third bullet, notice that the change in weight from 9 to 18 and the weight at age 18 coefficient in Model 1 have got exactly the same estimates. 0.048 for the change in a unit or a kilogram of weight at age 18, and notice that that impact is basically the same as increasing DW18 by 1 kilogram. You got to realize, if you're going to increase DW18 by 1 kilogram, that's the same as having the age 18 weight go up by 1 kilogram, holding the other information constant, earlier age information. And so it should make sense to you that the amount of soma increase is going to be exactly the same, because we've increased the age 18 weight by 1 kilogram, either because the change from 9 to 18 is a kilogram more, holding the age 9 stuff constant, or because we just increase weight at age 18 in model number 1. Another important issue covered in this section is collinearity. The definition here is that two regressors are collinear, x1 and x2 are collinear, if you can come up with constants C1 and C2 so that there exist values of C1 and C2 that can make a overall constant C0 for every one of the observations and the data cases for these regressors. And this is a way of saying that the two variables are linear combinations of each other. And this can occur quite frequently in regression problems. It occurs a lot in things like psychology studies, where there are many, many questions that all relate to the same underlying psychological construct. You can also see things happening like this when you study education data like ACT composite. Well, ACT composite is a linear combination of all of the components of the ACT exam. So if you have all the components of the ACT exam and the composite variable in a model at once, you have this kind of collinearity problem. And there will be some regressors that will be kicked out of the model and won't be estimated. We saw this happen previously in the DW, for the DW9 and DW18 variables back here in Model 3. They were redundant, they are linear combinations of the other variables and therefore cannot be estimated. We'll talk more about collinearity or multicollinearity in future work. What we're going to work on now is interpretation of effects. We'll start with the basic mean function, and we'll increase the predictor value x by a unit, and what you can see is that a 1 unit or a small unit change in x induces beta 1 units of change in y for a unit increase in x. And that's the basic interpretation of one of the beta coefficients. However, if a predictor or a regressor is measured in the log scale, or we've taken the logarithm of a predictor, how do we interpret what beta 1 means? And what I want you to observe is that if we take the derivative, or the change in the mean function, for a little bit of a change in x, what do we get? Well, the beta 1 coefficient is involved, but it's not just the beta 1 coefficient. It's the beta 1 coefficient divided by x. And so what this says is that as the regressor or predictor value x gets bigger and bigger and bigger, the effect on the mean function becomes quite small. But for small values of x, the impact on the mean function can be quite substantial. And so this is really the issue that you need to be aware of how to interpret when a model has a logged regressor. Here's an example from our M99 model. We had a coefficient in there, log of miles. And what does the effect look like on fuel consumption? Well, what you can see from this diagram, plotting the effect command for the miles term from model M99, is that for very, very high miles, the change in the mean function, or the change in fuel consumption, is quite modest. But if we have a smaller number of federal highway miles in a state, the impact on fuel consumption is more drastic at smaller values of x or miles than it is at higher values of x or miles. You got to realize that this is graphed in terms of the raw miles component, not in terms of log miles. And so this is the correct way to think about what the impact is on fuel consumption when we change miles. And that brings us to thinking about how to interpret an effect when the response variable is in the log scale. And so for the next discussion, we're going to be thinking about changing and altering the predictor xj by a unit. What happens to the response? Well, in this model, there is a linear mean function in terms of the log of y. For the moment, we'll talk about log base e, but there are equivalent statements for other base logarithms. The beta subscript parentheses j and the x parentheses j mean not the jth predictor. So x sub parentheses j means all of the regressors that aren't the jth one, and beta with the subscript parentheses j mean all of the beta parameters that aren't associated with j. And we're going to talk about what is the impact of changing xj. Well, we need to work out some of the math, and what I need to have you realize is that the logarithm of the mean function of y as a function of our predictors is approximately equal to the expected value, the mean function when we express it in terms of log of y. And that's not exactly right, but it's approximately the right thing. And if that's approximately true, then taking anti-logarithms, or taking everything and raising base e to those powers, anti-logarithms will get rid of this log on this side, and it will be e to this mean function on the right side. And then if we plug in what we know about the mean function for the log of y, which we expressed back here on overhead 22, we get e to the linear combination of the beta and the x's. And because e to a linear combination up in the exponent is because of adding the exponents for products, we have e to the beta j xj times this remaining term. And this suggests that an effect of xj multiplies the rest of the mean function as a multiple. So, please notice that you have got an expression here that involves xj, and it also involves the rest of the betas and the x's. Okay, let's go further. Now we're going to increase xj by 1, and on the left side I'm just taking a 1 unit increase in xj, and on the right side, everywhere there's an xj, I'm going to add 1. And so I did that right here. The rest of the terms remain the same. I will bring beta j in on xj and beta j in on this 1 so that I get an extra e to the beta j term. And the e to the beta j xj I put back into this linear function so that it takes the form of the mean function. And this final result tells you that one more unit of xj gives you e to the beta times the previous mean function when xj was a unit smaller. And so an additional unit of xj produces a multiple of the previous mean function. And this suggests that some kind of a percentage change interpretation is going to work. So I use these expressions right here, comparing e to the mean function for xj plus 1 relative to the mean function at xj, and you can make this change over the base percentage change expression. And simplifying, we can see that it's going to equal 100 times the e to the beta j minus 1, and we can get a percentage interpretation. It's going to go something like this. For example, if beta j was a 0.2, then this e to the 0.2 would be 1.2214, and if you plug that in right here, you get 100 times the 1.2214 minus 1, and that's a 22.14% increase in the response, or the expected response, for one more unit of xj. So you can interpret that in terms of a percentage change, percentage increase in the response. If the beta j coefficient is relatively close to 0, a modest size, something like between negative 0.4 and 0.4 as suggested in the textbook, then this part of the expression is very similar to just beta j itself, and so you can almost approximate the percentage change with the beta j coefficient itself. So if you saw beta hat j of negative 0.014, move the decimal place 2 places, and you might say that, well, the effect of xj going up produces a decrease in 1.4% in y. And that would be approximately correct. All right. Now, what if the response variable was in log scale and a regressor was in the log scale? Well, what we can do is we can use the same expected value expression for the logged response, and we can use what we've learned So let's go through this, how this would work. So consider that there is a regressor z that has been expressed in the log scale, so that xj is log of z, and if you replace z with a little constant c times z, the regressor is therefore the log of c plus the log of z. And so that means if we would increase a regressor by log c units, we could express it like we did previously on a previous overhead. This is going to correspond to, in our example, if we would increase the predictor z by 5%, that means back here C times Z, C would be like multiplying Z by 1.05. That is what it would mean to increase a predictor by 5%. If that happens, then C, of course, is 1.05, and then using the construction that we learned previously, you would have a log of 1.05 occurring right here in the inflation. And the log of 1.05, when we're doing base E, is 0.0488. So, for example, if you had a beta hat J, which was 0.03, and you increased the Z regressor predictor by 5%, this expression right in here would be e to the 0.0488 times the 0.03 beta value, and you'd come up with a 1.00146 multiple for the previous mean function back at the original Z. In terms of percentage change, that means that the change in the response moving this 2 decimal places is going to be 0.146% change. Not a very big change at all for this particular example. Here's a data example that we can use to illustrate these issues. We have some transaction data where the response variable is a function of time, teller time, minutes of labor to handle bank transactions at a bank branch, and we'll be analyzing this in terms of the logarithm of these teller times, base E. Our first model, Model 1, has the number of Type 1 transactions and the number of Type 2 transactions explaining this response. The second model has Type 1 transactions in the original linear scale, and it has the natural logarithm of Type 2 transactions. Here are the coefficient estimates for both Model 1 and Model 2, and we're going to go through interpretations for these. So first of all, let's take a look at Model 1 and interpret the T2 coefficient. So Model 1, remember, is we have a logged response, and we're going to interpret a unit increase in Type 2 transactions. In other words, one more transaction. What does it mean? Well, if T2 goes up by one more Type 2 transaction, we know from a previous overhead result that the processing time is going to go up by e to the beta hat 2 multiple. So whatever the previous teller time was, teller time will go up by this ever so slight inflation factor. That's not terribly interpretable, so what we could do is use the percentage change interpretation, and one more Type 2 transaction means we will get 100 times e to the 0.00379 minus 1, or in other words, about 0.0379 percentage increase in teller time. So not even a 1% increase in teller time for one more Type 2 transaction. And I think this is reasonable to think that just one more Type 2 transaction, when there might be dozens or hundreds of them in a day, is a quite reasonable expression for how much percentage increase there would be in teller time. For Model 2, when the Type 2 transactions are in the log scale, you could say, well, what if the number of Type 2 transactions would increase by 5%? That means that constant is a multiplier of 1.05, and that means the inflation term would be e to the log of 1.05 times beta hat 2, and beta hat 2 here is 0.83427, and so we get an inflation that is quite a bit bigger, 1.04. And in terms of percentages, 5% increase in Type 2 transactions is going to result in a 4.16% increase in teller processing times. And I think that's reasonable to think that 5% more Type 2 transactions would increase the teller time by maybe nearly that amount, almost 5% increase in that as well. After all, it takes time to process transactions. One of the final things we'll do in this unit is talk about, well, what if we would leave out a predictor? So in this overhead, we have a mean function that is a multiple linear regression mean function with a component for x1 and a component for x2. And I want you to try to understand what would happen if we left out the x2 part of the model and we only used x1 to explain the response. What is going to happen? Well, if we look at the mean function only in terms of x1, we take a repeated expected value to get an expression, and you can see that what we get is the same beta naught intercept plus a beta 1 times x1 term that will still be involved, but beta 2 is going to multiply the mean function of how x2 relates to x1. And so this is the crucial piece. And what I want you to see here is that if x1 and x2 are related in terms of a linear function or no relationship at all, analyzing a mean function that only has x1 in it is not going to be terribly misleading. However, if x1 and x2 are related in a more complicated nonlinear fashion, then a mean function that only has x1 in it is going to be very misleading. So this is why we will always be looking at scatterplot matrices of the two predictors with each other, because that tells us something very important about the problem. If we miss a predictor, what will happen to our inference about the remaining one? Another way to look at this is in terms of the variance function. What happens to the variance function of y if we get rid of a predictor or a regressor x2? And what you can see is that the original variance function was just sigma squared, and if you get rid of x2, it probably doesn't matter very much if the two predictors are not very variable in their relationship with each other, or if the effect of x2 on the response is really quite modest. This quadratic form multiplying here will be small, and so it's quite possible that the variance function won't be very far wrong if the variation between the predictors is sort of small. Another thing that I've talked about before in this presentation is the issue about whether we have experimental control over the regressors or whether it's an observational study. You really cannot make causal inference statements if the data are observational, like in our fuel consumption problem. They really need to be actually controlled and experimentally changed in some sort of controlled environment to really build a causal inference model. Observational studies are usually the ones we do because they're available and they're often inexpensive and can actually be done for ethical reasons. The problem with observational studies is that there are always really potentially dangerous problems with lurking variables. Variables that were not in your study but have a very important impact on the mean function. So if you've got a lurking variable and it's correlated with a predictor in your model, you can often get very incorrect and inappropriate inferences about the predictor in your model. So to avoid that problem, there really isn't anything you can do except try to design your study to capture the important lurking variables. And if you can't capture the important lurking variables, at least try to obtain your data in some sort of random fashion, so random sampling, so that lurking variables will be balanced throughout your data collection process. The final issue we're going to mention here is R squared. We've talked about it and used it in some of our problems. I want you to be aware that R squared can be influenced by the distribution and the arrangement of your predictor set. So if you have very widely dispersed predictor values, like some of the ones we saw in our fuel data, R squared can be artificially high and artificially inflated and not really provide an accurate representation about the strength of relationship between the predictor set and the response. There is a way to get a graphical representation of R squared and strength of model from a scatter plot. And so there is a way to visualize R squared for a multiple regression model. Basically, it amounts to plotting the observed response values against the fitted or predicted response values. And we've done that here for the model M1 for the somatotype data using the weight at age 2, 9, and 18 for the Berkeley Guidance Girls Study. And in this display down here, we're plotting the actual somatotype values for the girls against the model predicted ones. These are the Y hats down here. And you can see that the Y hats are a pretty good representation for the actual soma values. And so this is a suggestion that this model is fairly effective. The model predictions are reasonably matching the actual soma values. Let me know if you have questions.